Hi everyone, my name is Fernando. I know a lot of people, there are a lot of new faces. I'm really glad that you can join us today for this event. And when Ramon reached out and was like, hey, we would like to do this event, I was like, what should be my talk about? And we were like discussing yesterday during dinner on how impressive it is that here at Penn, we're always like 5 years ahead of what is coming. So I want to show you a little bit of an overview of the things that we have done, when we did it, some of the content I'm going to show. Some of you here in the room have done this work, so I'll try to give as much attribution as possible. But yeah, that being said, we're gonna start. I'm a fifth-year PhD student here at Penn. I've been here for a bit too long, so if you see Vijay today, tell him that I should graduate already. I work on autonomy, perception, UAV hardware. Before joining Penn, I did a lot of embedded systems, but now I'm rotating into a robotic systems engineer. Previously, I was at Samsung AI in New York. It closed, unfortunately. Bell Labs, the one in New Jersey, and I also had a small consulting company. And the outline of this talk is going to be, first, I'm going to talk about GRASP and robotics in general, for some of you who don't know what GRASP is and what do we do. UAV history at GRASP, what projects were done here in GRASP Lab, some current projects, future work in progress projects, and also some Q&A if we have some time in the end. Let me check if I started my timer. I didn't. Good. So what is the GRASP Lab? So the GRASP Lab is the best way of understanding it. It's an umbrella lab called the General Robotics Automation Sensing and Perception Lab. We roboticists have this fixation, and I think computer science people in general, to look for good acronyms. I think this is a pretty good one. And this is an old picture of GRASP, which is quite iconic. I think the computer on the back is the ENIAC that is here a couple of blocks away in the Moore building. And you see here a couple of all-time geeks, and the person in the middle is Dr. Rusina Baichi. She founded the lab in 1979. And right now, GRASP is composed of 25 faculty, 137 PhD students, 265 master students. So it's a pretty big lab. It's currently ranked second in the computer science rankings for robotics. We're head-to-head with Carnegie Mellon. And we have a lot of startups that are issued from GRASP, such as Exim Technologies, Ghost Robotics, Puro, Vertic, and Camel Robotics. So I would like to take some time and talk about Rusina, because I think that she's like a badass character in robotics. So I was reading her biography, and it's pretty amazing that she was born in the 30s in Czechoslovakia. And her parents were murdered during the war, but he was able to go to school studying electrical engineering. She got her master's, and then she was named enemy of the state in Czechoslovakia, so she had to go and work in a factory for 5 years. After doing that, she came back, got her PhD, and after that, she started working with Stanford, got a second PhD at Stanford. And you know that you are this kind of character, you have this kind of like super amazing personalities, not because you have 2 PhDs, but because you are in a set of playing cards. And also, you have this little toy with like a wobbly head with your name. So Rusina is kind of a big deal here in GRASP. So you may be able to see, I don't know, I don't think she's going to come here, but if you see her, it's a very interesting person to talk to. She's back at Penn after like 20 years at Berkeley. So yeah, really interesting character. So this is some of the faculty we have here at Penn. And I also wanted to say kudos to some of the staff, admin staff that helped run this amazing lab. And these are some of the locations that we have. So this is the Penn Innovation Campus where you guys are right now. It's a great place to do field robotics, mainly because if things crash, there is not as many people as in main campus. So we can do drone ground robots experiments here. We have the Schuylkill River flowing on the back of the property, so we also ran experiments with boats there. So it's a great experimental location, but we also have lab space in the main Penn campus, in the Levine building, and now in Amy Gutman Hall. And something that I think is really cool is the Grasp on Robotics seminar on YouTube. So this is a series of talks by academics and also industry people that is quite exciting. So you can see a lot of like very cool talks on YouTube, and they're like all recorded. So I'm gonna, oh, these screens are not great. I'm gonna start talking about some of the beginnings of how we did aerial robotics. And we didn't start with quadcopters because this was way before quadcopters were a thing. So aerial robotics in Grasp started around 2003 with these small airplane models. If you go to the third floor, they are hanging from the ceiling. And also with this blimp, which was a quite big thing. So this huge thing was able to carry around 3 kilograms, 6 pounds, with a Pentium 3 on it. So at that time, this was a big deal. So they flew it in the main football field that Penn has in campus, because they didn't have any space to put that huge thing. But they were running a companion computer on board that had this ROCi, which was a predecessor of ROS on board. So yeah, and you can imagine what happens if there is a little bit of wind with this big thing. But they published papers. They managed to publish some papers on computer vision too, with like this plane. It's a pretty amazing achievement, if you ask me. Then around 2010, quads starting to be a thing, and Penn did one of the biggest contributions on quadcopters by creating controllers that were able to do aggressive flight. So this is the work of Dan Mellinger. I think Alex is also here in the room. These are some of the early projects that work with quads. And they were able to do these aggressive maneuvers where the quads are like flying like through hoops quite fast in this room. But there's a catch here. So if you see these like red lights on top of the video, that is a motion capture system. So essentially, the UAV doesn't have any idea of where the obstacles are, and it's relying on these cameras to like get the location of the UAV in real time. So the next big thing that happened like on top of this was reduction in size. So let's see if I can go to the next slide. So this is one of the clips that convinced me to join Penn, and I have here a little piece of history. So this is Alex here worked on this. So I think this is one of the first small drones before the Crazyflie was a thing that was able to run autonomously, as you can see in these videos. So they did a series of pretty cool videos, got a lot of attention, and this attracted a lot of interest into UAVs. But as I said, the catch with this was that they were running this in a room with these cameras, and if you want to do this in another location, you need to bring these cameras. So that is not ideal if you want to have an autonomous system. So the next big thing was fast lightweight autonomy. So this was a DARPA project. DARPA usually has challenges, for those of you who are not familiar, that are like, I'm going to toss a challenging problem into the community, and I'm going to have teams submit their solutions. They usually set test benches in like really nice locations. They do it like really well. And then you test your solution, and you get ranked depending on how many points you got. So to grab the same quads that were flying in the lab and take them outside, we need to solve a few problems. State estimation, that means where your quad is right now. What is the position, and orientation of your quad. Obstacle avoidance, so if there is something in front of you, you don't have to run into it. And also onboard computation, because you need to do all this on board. There is no radio link that can transmit information to to the UAV. So these problems were solved with these three components that you may be familiar today. VIO using LiDAR and motion primitives for obstacle avoidance, and also putting a Nuke computer on top of the robot. So this was the prototype that the team FLA team put together, which looks pretty much like a computer with a few props. But they were able to achieve really, really good results with this. So this is one of their videos in which you can see here, you have the ARVIS representation. That is a satellite, like a Google Earth overview. And you can see here how the drone is like flying on its own, avoiding some of the trees. And they need to look for a way to enter this building here. So the quad first goes around the building looking for an opening. Then when it finds that one of the gates is open, it gets into the building and it's looking for the one of the objects of interest. For some reason, the military is really obsessed with barrels, like red barrels and blue barrels. So here the target was one of these orange barrels. So pretty amazing feature. And this was the beginning of the autonomy stack that we use here in the lab for a lot of the experiments that we're running. OK, so the cool thing about FLA is that it brought a lot of innovation into the UAV space. So you can see here a progression of the different platforms that we had, from the big one with a heavy LiDAR on top to the smaller Falcon 250. And we also collaborated with Open Robotics to develop this computer vision platform that was called the OVC. So that had synchronized imagers with IMUs and was able to provide or help provide state estimation for the UAV in a compact setting. And then the next goal was to scale down. So we have this platform that can do all this, but it's kind of dangerous if we want to use it indoors. So if we want to be safer, we need to go down. So this is the work of Dinesh is here in the room. He was working in these projects. I have some of these quads outside if you guys want to check them out. So this was the inception of the original Starlink that then Model AI improved into and manufactured into the prototype into the product that they're selling right now. But you can see here the different sizes of the smaller UAVs that they were using. And these were using the Voxel, the first version of the Voxel computer. So this is a very cool video of what these platforms were able to do. And compared to the previous videos where we have this aggressive flight, in this case, the platforms were using onboard state estimation to go through narrow gaps like this one. So just to keep things in context, this paper was published in 2016, I think. So yeah, 2016. So it's almost 10 years ago. But these small platforms, usually if you want to go small, the only way of doing it is going with cameras or time-of-flight sensors. And that has an issue is that usually the perception sensors are not as good as if you go with bigger LiDAR, automotive-grade LiDARs. So we put together this platform also in-house. It's called the Falcon 4. And it's essentially a flying LiDAR and a flying computer that we are mainly using for applications in forests. So as I said, a big LiDAR is really good. It gives you really accurate depth. Range can go up to 90 meters, 50 meters. But the challenge is that you are essentially flying half a kilogram, more than a pound, only on the sensor itself. So for the smaller quads that we have here in the lab, we rely on the RealSense or PMD sensors, time-of-flight sensors, to get obstacles around the quad or get state estimation. So this quad enabled this work that was autonomous flights in forest. So we worked on this on 2020, 2021, Come on. Great. So this is at the Wharton State Forest, 1 hour away from here. And we're able to fly under the canopy, avoiding all the tiny branches that these trees have. It was a very challenging environment because you also have your state estimation gets messed up, and because there is undergrowth that is like moving constantly. But the system worked quite well, and you can see here how the quad is like finding the narrow gaps in between the trees to fly in this challenging environment. And the cool thing about this experiment is that we were also at the same time as we were flying with measuring tree diameters. Yeah, I think I'm good. Measuring tree diameters. So when you finish the flight, you have a 3D map of where all the trees that the quad was able to see were located, and what was the diameters of the trees. So this is part of an ongoing effort to do precision agriculture with UAVs, but precision forestry with UAVs. Then this platform also enables some research on air-ground collaboration. So here you can see our Jackal platforms and also the Falcon 4 UAV. So in this configuration, the Falcon is flying a high-altitude mission at around, I would say, 100 feet. And it's building in real-time a map underneath. So this map is a semantic map, so different colors mean different semantics. So blue is road, red is building, green is trees, dark green is grass, and so on. And we're able to transmit this map in real time to the ground roads so that they could plan their mission, localizing this map and plan their mission. One of the challenges of doing this is communication. So when you are in this kind of unstructured environments and you need to communicate between the different robots, there needs to be a way of like having a communication system that can break and reconnect. And if a robot goes rogue, there needs to be a way that we can go and extract information from that robot so that the whole system works as a team. So this is an after-the-fact animation that we did. So here you can see how the quad is like literally, when it changes colors, it's like transitioning to a mode that is like, all right, I need to go to that robot to pick up some of the messages that robot has produced because I haven't heard from that robot in a while. So let me move it a little forward. Yeah, so here you can see the quad is exploring, and then at some point it's like, oh, I need to go talk to robot number 1. So it talks to that robot, transitions into a communication phase, does a flyover, extracts all the information, and then flies away to continue its mission. Event cameras. How many of you are familiar with event cameras? OK, so I'm going to spend much time, but the cool thing about event cameras is that they work in a different way compared to traditional cameras. So in traditional cameras, we have the concept of a frame, which is essentially we're sampling all the pixels at the same time. The event camera works in an asynchronous way. So each one of the pixels that changes is triggering an event. So instead of having frames, we have a continuous stream of events. And the main advantage of this is that they are faster compared to traditional cameras. And also, each one of the pixels triggers independently. So there is no concept of global exposure. So if you try to take a picture towards the sun, something that you will see is that your phone needs to adjust exposure such that the whole image has a contrast, an exposure value that is the same for all the images, and that is going to blind you for watching things that are not like the same level of brightness as the sun. With an event camera, you can have that. You can like point an event camera at the sun and see things in the same scene, even if they are in the darkness, which is pretty cool. So we put an event camera on one of our high altitude UAVs just to see what we could get that we can't get with traditional RGB cameras. And this is a video that shows an experiment here at Pennovation. And I would like you to, I want you to look towards the bottom right. So you see an area of like high exposure there that when we transition into the event camera feed, all the details appear on the ground that you can't see with the traditional camera. So we also performed flight in the like at night or during the sunset, and we show that event cameras are able to recover a lot of information in these challenging light conditions. But there are still some noise issues that needs to be fixed with these sensors. And finally, I would like to, this is also another project that we're working on, trying to have a full UAV working with event cameras. So Dexter here is leading this effort. And finally, I would like to talk a little bit about foundation models in robotics. I know that we're in the AI era, and this is happening for a lot of things in robotics. So these are the aspects we're looking into to do with foundational models. So high-level specifications of missions, of goals, scene understanding, problem decomposition, depth estimation. These are things that these networks are very good. So for instance, if you tell your robot, you give this high-level goal assist in this scenario, the robot is able to plan a mission from that high-level specification and perform the mission. And also another cool thing is using VLMs for scene understanding. So in this video, we have a high-altitude UAV that is flying, and you can see the kind of labeling that we can get from the objects on the ground. And with these labels, we can construct semantic graphs that then we can transmit to other robots on the ground, so then they can perform different actions. So with this, I would like to finish, and I think that we have some time for questions. So yeah, thank you. All right, any questions? Good. Yes, please.
The event cameras.
Yeah.
Do you know of one that is already on the market that you use as like a sensor, or like just 'cause I know you had some stuff listed as a lidar. Lidars you listed as actual ones that you used. What different event cameras have you?
So right now there are, I would say, two main manufacturers of event cameras. One is a company from Switzerland called Inivision. The other one is a company from France called Prophecy. They both are selling sensors, and they sell sensors with different resolutions and with different capabilities. So I think that this is a very novel field. So you will have to do some exploration on what are the applications that you want, because, for instance, for some obstacle avoidance, low resolution event cameras may be better, because there is a trade-off of like how many pixels or events can you extract from the sensor if your resolution is very high. High resolution event cameras are better for mapping because you get more spatial resolution. But yeah, you can buy these sensors if you want. One of the Bern is one of the persons that maintains the ROS drivers that work quite well. But yeah, you can buy these sensors off the shelf. Yep.
Hey, Fernando, thanks. Can you speak to how you performed SLAM in this forest where it was pretty featureless and very symmetric, and a human could easily become disoriented in this forest?
Yeah, that was like one of the main goals of this work, and that happens 100%. If like I put you in the middle of the forest, even if you walk through, all the features that you're looking at are like really similar. So like all the trees like look really similar to you. But for the drone, it can measure accurately tree diameters and also the orientation of the tree trunks. And these two features are good enough so that you can do SLAM with them. So I guess that the answer is the drone is way better at estimating these metric features compared to what you are. And that's how we can do SLAM with these systems.
We've got time for one more if you got it.
All right, yes?
Thank you. Great presentation. Absolutely loved it. I just have a question on one of the last things you touched on, which is the AI route planning. Is that more of would you say it's a mix of existing GIS data that is used for like traditional waypoint planning and a mix of what's on board, or is there other GIS databases or other databases that the aircraft can pull from in advance to automatically plan out the route?
So we try to run most of our experiments without priors. So, and I showed this in some of the mapping experiments. the only thing that we gave all the robots when they start the mission is we told them like you're starting from the same position. But that was it. The mapping example that I showed with the semantic map, essentially the map was built in real time on the quad, and it was transmitted to the ground robots that would like use that map to plan their actions. So you could use some priors if you want to run missions like this. And I think Ian, that was one of the authors of the work, did that. But you don't have to.
Thank you.
You're welcome. All right. Thank you.